All right. So this is our weekly seminar, and we are starting today with a classic published in 2005 by Ioannidis, a famous statistician. This is basically a very straightforward statistical model of the scientific process, like very straightforward, very standard. And like if you just write out the equations, you get a bunch of free variables, and then you like plug some plug some numbers which look reasonable inside. You run some simulations, and you get to the headline claim. Right. So I think I'll go through the text. I'll maybe skip the complete derivations, but like we can address them if you have a particular question about them. Oh yeah, and I first heard about this paper in my statistics class. It was a homework. Right. So like the claim that for most reasonable free variable values for most designs and settings, it is more likely for a claim for a paper to be false than true. If you grant that, then we can expect that most research fields in the aggregate measure bias rather than ground truth. So this paper was published in 2005 when discussing when it was in fashion to bank on p-values and say that Bayesian statistic is so much better. And I think this paper operates it takes the p-value framework just because it's standard, but its claims aren't really limited to that. I guess I'll start introducing the formalism now. One parameter we introduce is capital R. It is the ratio of true relationships to no relationships in the field. For example, if capital R is 0.5, then there are as many true relationships as non-existent relationships. And this is an a priori value. This is we should expect that, for instance, in genomics research, where we have tens of thousands of genes, we should expect many we should expect some relationships, some relationships, and in fields I don't know, maybe physics, maybe particle physics, I don't know. We should expect few actual relationships.
What does your relationship mean here?
Relationship means it's just a word for something that exists. Research papers often talk about this factor influences this factor, and this is what relationship stands for.
Okay.
So this is basically just a claim, of facts. You might say that there's a hypothesis space, and this is a hypothesis.
Yeah.
Right. Then we take if R is the probability of if R is the ratio of true relationships to no relationships, then the a priori probability of given relationship or given hypothesis is that it's R2 to R plus 1. This is easy to see empirically. To see, just to see. For instance, if we plug, if we plug some reasonable numbers, so I can zoom that. This is a question. If you have no two relationships, then R to the R plus 1 simplified to 0. If you have all the relationships, then it simplifies to 1. This means that our a priori probability is 1 because all the relationships are true. And if the ratio of true to non-true is 1, then the probability simplifies to 0.5. So this is just algebra. Nothing going on here. Then you take a type 2 error rate, you take type 1 error rate, and from our standard table, we derive our value of interest. Our value of interest is how many hypotheses are indeed true. As in, we conducted a study, and the study came out positive, and the fact is also positive. So this is just joint probability. And we can write it as true positives over true positives plus false positives. And if you just plug the numbers, then we get this thing here for our target value. And this gives us our usual relation between the type 2 errors and type 1 errors, which is that. And as we typically pick 0.05 for type 1 errors, then this is what this boils down to. And so far, this is standard. And I think we might have we don't have a figure for this yet because this is just standard. And this is our formalism, and so far so good. Now what we do, we introduce a bias term. Bias term is research manipulation. And for simplicity, we take the bias term to be independent of R, or of anything really, just an independent variable, because the researcher might want to fudge the numbers anyhow. And we just rewrite our previous results with the bias term. And this is something we can work with, as in we can start to plug some reasonable numbers and run the simulations. And I think this is what the figure does. And so let's try to decipher this. We have plots for different study power. This is power 80, power 50, power 20. Power is basically a relation between study size and the hypothesis being tested. So this is how much information a study could hypothetically extract.
And what is power, the original formula this was described about? Do you know?
Power is it's somewhere in the relation between type 1 type 2.
Oh, okay.
Yeah. Um, right. And the different numbers are different values of bias. And so if you take powerful studies and plot like this is our like target number on the y-axis, and the x-axis is a priori probability. Then like what we get is that it might be useful to look at it across different powers. What do you think we get here?
Right. Yeah. I mean, power doesn't seem to really matter when R is low. Like if R is really low, then it doesn't matter what kind of a study we do. VV is still low. But then also at some point, I'm not sure what one big conclusion to give here.
Right. So I think the one thing that's happened here is that as we vary bias, we can we can shift our target number by a factor of 4, right? Yeah, so like one way to interpret this. First, we look at pre-study odds. If pre-study odds are extremely low, then we don't get much of an increase post-study because we just need a lot of evidence to update ourselves, right? If pre-study odds are high, this is pre-study odds 1 is like 100%. 100%. Pre-study odds 1.
Oh yeah, pre-study odds means only 80% of post-study probability.
Yeah, like this implies that we actually lose information here, right?
It's just hard to analyze a graph when there are essentially 4 axes. It's like even more, right? So it's X, Y, then colors, then the power, and then the distribution itself. So it's
the indeed 4 parameters here. And like this is our basic simulation design. Like we just we vary our a priori numbers and try to make sense of the distribution that comes out. And we can do another variation on the design. We can try to consider a situation when a research field is hot and a number of teams are racing to get some results out, racing to publish. And in that case, what was that? So this was our previous PPV. And in that case, we basically just like put on a term of n, because we now have like n studies going on, like n random trials. And this decreases our target number, unless we uphold this condition.
But does it decrease the target number because teams are more likely to be like biased to push first?
This is because like to get sane hypothesis testing, we ought to uphold a particular like type 1, type 2 error rate balance.
Yep.
And if you don't, then
So I get it algebraically. I just don't understand that like empirically, because if the bias doesn't change and we just have more independent research doing the same thing, then why would PPV?
Yeah, all right. I guess so it was a bit confusing. This is this derivation is before bias. So this is defined. This is derived from basic PPV.
Okay. But why would PPV decrease with more research?
Right. This is like have you heard of multiple hypothesis correction in testing?
I might have heard of it, but I wouldn't replicate it.
Yeah. So the idea is that if you all right, so like if you're just fitting an estimator, like say you're like dropping a coin and you want to get the probability of a coin, then more data is good. But if you're testing like because you always converge because you have this property of convergence. But for hypothesis testing, this may or may not hold depending on the nature of hypothesis or something like that. Like for example, you can imagine a distribution which is like, I don't know, skewed to the right, but it's but your target value. I mean your target function of distribution lies in some the property you are trying to find is in that place or something, and like independent. Oh yeah, I guess this is important. Here we have independent trials. Like we are not putting information.
Yeah, that I understand. But yeah, I get your example about scripting. Again, what's the keyword to go to? Multiple hypothesis testing?
Bonferroni correction.
Again?
Bonferroni.
I think we can.
Yeah. Okay, this might have been a little heavy on statistics or like out of the blue. So let's try to go on this lightweight corollaries in both. So like if you just like look at the formulas, like we have a bunch of free parameters, as I said, and like we can just we take the formula and like differentiate by n or differentiate by beta and so on, and we take a bunch of takeaways from that. And one takeaway is that smaller studies have smaller power, and smaller power implies less information from each particular study, and therefore our PPV goes small, and therefore the probability of this area giving us any useful information wanes as well.
Okay, so it means like if we do bad studies, like small, low power studies, then we kind of there is a high probability of introducing false relationships into the field, and then other research can build on that, on false assumptions, and also be false. And this is like
but like you are suggesting a second order effect, while I'm talking about the first order effect.
Yes.
Like
just small study is bad.
This is bad, and you can ground that down into like an equation that fits on one line.
Mm-hmm.
Yeah. So like you just like differentiate the same, you get this corollary. Like I mean, people often talk about small studies bad. This is algebraically wide. Yeah. I think this is kind of the same thing. Only here we're talking directly about effect sizes, and here we're talking about study size, which is upstream of effect size. And but this has more maybe more like attractive examples, because when we measure impact of smoking on cancer, we get an effect size of like 10 or 20, as in people who smoke are 20 times as likely to get cancer. Very high effect size. You don't have to do any kind of statistics to find that. You just like plot. And then you have genetic studies again, and in polygenic genetics, when you try to find like 5 genes which, when taken together, contribute to something and make something 5% more likely. Like you have, I don't know, you have say 100,000 genes, you take like combinations of 5, you get an enormous number of combinations, and then like you need to find a 5% increase in something, you need enormous study power to find that. And to get enormous study power, you have to have like a mind-numbing study size and very low bias in each instrument along the line. So this is what makes the field hard, again, like from simple first principles. All right. Then I guess like this is also well known. Like if you pre-register what you're looking for, if you're only looking to confirm a specific hypothesis, then you're more likely to find a true result, maybe a true negative result about this hypothesis, than when you're going on a fishing expedition to like explore the data and try to find something. And this is because like this influences R. Because like if you're trying to confirm something, you have one R, and if you're trying, if you're trying to confirm a specific thing, then you have like one kind of R. If you're just trying to find something, then your R basically tends to infinity. Like the probability that you find something tends to infinity, but like this might not bear relation to like to ground truth, if that makes sense. I guess this paper might be more useful if rewritten such that each corollary has like a term in the equation I could point to. Okay. So again, kind of similar thing to corollary 3 is that if we are flexible, then we have a lot of leeway to smuggle something. And this thing here increases U. So like this was R, and this is U. Okay, this is about how we can misreport something. Like, for instance, like have you seen funnel plots? Funnel plots. Let me show you funnel plot. So like what you can do in meta science is it's got like the x-axis. Yeah, so is it essentially plot studies such that on the x line you have reported alpha, and what you often get is I guess they only show in nice funnel plots. Oh yeah. And what you often get is something like that like all the studies which are published lie on one side of the line, which seems implausible if you like consider that they are like drawing from random. And this is how publication bias looks like.
Yeah, it's like shifted to the left from the
Right. Cool. Yeah. Then, like, I don't have particular highlights on corollary 5, but also sometimes, like, I think this is most common in pharma. Like, I don't know, like, it is often the case that affiliated researchers publish stuff, and they tend to have high bias for some reason. And the next corollary is perhaps more interesting for us. Like, when I was reading corollary 4 about flexibility in design and corollary 6 about a hot scientific field, like this reminded me of our field a lot. So, like, the way that corollary 6 goes is that it is like basically this formula we saw above with the power of n, and like, yeah, I think this is the same. This is the same, but the colors being different. So this is blue is N1 and yellow is N50. And what we are seeing is that, like, again, algebraically, if you just like plot across list of numbers, the more independent studies you have, the less a chance of each particular study being true, like aligned to ground truth across a number of study powers. And I think what's most interesting here, if we compare these plots, is that high number of studies effectively reduces, if I just zoom out, like, so this blue line here is kind of like this red line here, which means that when we increase the number of studies from 1 to 5, our effective power dropped by 4. Something like that. Mm-hmm. Right. Also, like one fun tidbit, apparently this is like a word in meta science, like a known phenomenon in meta science, is that when a field is hot and someone publishes a positive result, then people who previously found a negative result on the same thing and have been holding out because like it's stupid to publish negative results, like debunk it all the way. And then you get the opposite again.
Oh,
and apparently this is why like some fields, like some, I don't know, some medicine field, some biology field, like oscillate weirdly for a bit. Okay.
was that effect called?
Proteus phenomenon, apparently. I've never heard of it before this paper, but then I'm not a meta science researcher. Right. So I think we're about at an end of what I want to talk about. A few more examples of the simulations. So it's quite perplexing that in this statistical breakdown in this algebraic framework, it's quite hard to get the number of to get the probability of a research finding truth and being truth over 50%. This is hard to get. let's like look at a few choices of R which we can take, and then see like what happens with PPV. Like if you have a good study, like high power, high quality study, and our R is a priori probability is 50%, then our PPV becomes 85%. And if we, I maybe skip to the table right here. And like this is like the summarized in table form. So on the left hand side, you have power. Then we have a priori probability. Then we have bias, and this is our like target number we get. And like if we have a great randomized controlled study, then we get 0.85. If we do a confirmatory meta-analysis of good RCTs, this has high power but less a priori chance, and we get the same. But like if we by a little bit like if we decrease things just a little bit, like for instance we are reviewing not very good studies, which is extremely common in medicine, then our if it drops dramatically. If we look at clinical trials which have small sample size and that performed well, then we get something worse again. If we don't perform them well, we get something worse again. If you go from confirmatory to exploratory, then we are low again. If we have small sample size for exploratory, we get into 10% territory. And if we just go on a fishing expedition, then we basically don't stand a chance. Even if you limit the bias. So like independent of bias, whether it's 0.8 or 0.2, our PPV is like at this point basically not different.
Wait, were you saying that like exploratory research has more PPV previously? No? Am I missing something?
Yeah, exploratory research has like this term here increases or maybe decreases if you look at the fraction, because what's going on here is you basically go out in the fields and flip 1,000 coins. Like indeed many of them.
No, I mean like if you take just some data and like look at it honestly and trying to be honest, I mean, like, what can I derive from this? Shouldn't the PPV be like higher than if you look at that data and be like, how does this prove what I want to prove?
So I think this is like so what you're saying is, what if we have low U and the lower two rows answer that exactly? This is what happens. You get like a 5 to the 10 to the minus 4th increase.
Okay, so
and why that is because you look at like if you pre-commit to a hypothesis, like a priori in your data, you say I'm going to test this. Then you're in a confirmatory setting, and you have good R. And if you just like, here is some data, I wonder what I can find, then like you might be very rigorous about what you find, but consider that the data is a sample. It's not like population data, it's not ground truth. And your sample is going to be biased. And what you're gonna do is, if you operate in frequency statistics framework, which is this, you say like, I guess my PPV like just went to hell. And if you operate in the Bayesian statistics setting, you try to think of a distribution you sampled from, and like you try to kind of pull the bias all the way through, and then your output number will have error bars.
It still doesn't connect to me like empirically, but I guess I'll have to look at the paper. So it's just that I would expect, if you look at the same data with like one mindset is, I have this data and I will look at it trying to prove what I want to prove, we have more chance of making a false positive. And if you just look at the data and be like, what does this data say to me? But this suggests otherwise.
So this framework decomposes the two. Like when you talk about mindsets, you're talking about additional bias in terms of this framework. And when we're talking about hypothesis testing versus exploratory research, we're talking about the odds in terms of this framework, a priori odds, I mean. Yeah, I'm not sure I have like the thing about a priori odds is that you have low a priori odds of finding a new true hypothesis and a bunch of data because your data is a sample. Like one way you can interpret this is if you fix a hypothesis first and then get some data, then you have a pretty high chance of your hypothesis test on this data being false. But like if you're looking at maybe what's going on here is that like when you have good R's, we might get false result, and like this is just what we get. And when you have high R's, maybe what this is telling us is that this implies that we are looking for actual true hypothesis in the given data. And so like this basically what this is saying is that here this is a chance that you get evidence for your hypothesis, and this is simple. And here you are formulating a new hypothesis, and this is hard.
Yeah. Okay. So yeah, that makes sense. That also makes sense. But then kind of a bit of a misleading table, because that makes sense, but then it's kind of different questions encoded with kind of the same numbers.
Yep. If you'd like to check the paper, I invite you to check this green box here. I'm not going to go through it now, but like it might be useful as an example. Great. So a final thing maybe to say here, two final things. One is yeah, I mean, I've kind of got that about here. I'm sorry, but I don't know of a better way to discuss a statistics paper without, losing all the formulas entirely. And I think the beauty of this one is that it connects the high level claims to pretty simple formulas, really. So the formulas are kind of full of jargon. This might be a problem. Anyway, a few minutes to finish that. We can imagine just another way to look at the plots above. We discussed that we are losing information here, and what this implies is that if we get a null field, where how do we define a null field? If we imagine a field where there are no true findings at all, like in our setting, I think this is something about R. This is
so R is 0.
Yeah, this is R0, and what we should expect is that all our observations vary around 0, plus minus bias, right? Mm-hmm. And so in this kind of field, we should expect everything always to measure bias, because our ground truth is null. Mm-hmm. And furthermore, in this kind of field where the ground truth is null, if we get an extreme outlier result, if we get a very high effect size, then this is literally just high bias. And I think what Ioannidis is suggesting here is that such fields might exist. And we can, and this paper was published before the replication crisis. Yes, I'm just saying. And I think what he suggests people to do is this thing which I mentioned about Bayesian statistics, when we try to come up with prior distributions for the places we sampled from and try to pool bias all the way through to get to error bars. I think. Not even error bars, but rather the distribution and our sample in the distribution, which is very different from this framework, I suppose. Yeah. That's the paper. I guess the summary is that this is one of the standard decompositions we do in we do the same way you might decompose empirical risk or something, and this allows us to draw some surprising conclusions, I guess. I think the primary surprising conclusion is that I think I also saw a version of this paper. This one doesn't have it. I also saw a version estimating this numbers here for some popular fields, because you can at least eyeball them. Physics you expect to be different from psychology, stuff and things. And this gives additional sting to the claim that we should expect most studies, generally most studies, to be false. I think for fun, we could also try to eyeball these numbers for our field. For instance, for the field of jailbreaking literature. And I expect this to go, I don't know, to extreme hell. like they don't even do real hypothesis testing there, I guess. So we could try to fix it. Like, hypothesis is that this jailbreak gives attack success rate of higher than 0.9. Yeah. So like if you look at some of the fields we operate in, for instance, jailbreaking research, then these are purely exploratory, like which means that we are operating with this number, not this number. Multiple teams racing to the same result, factor of n. I mean, like I fully expect people to fudge the numbers. So I don't know, take bias of 0.5. So it goes to hell extremely quickly. That's what I wanted to say. I think this might be a useful thing to talk about in our critique of jailbreaking research. This point. All right. So, would you like to quickly talk about probe sync before we take a break?
How are you feeling, guys? I can do a...
Is it going to be mass heavy? Sounds like yes.
No, not really, no. Actually, no math at all, but some cool graphs on... But it will be about benchmarking.
Let's say with short. All right.
Now, the question of this is, how likely this paper is to be false? There we have it. But at one point, I want to believe that, like, 1 out of 1,000 jailbreak studies actually is somewhat true. But on the other hand, I think that, at least from the quick presentation of this paper that I've seen right now, they do have some ground, like simple math that sounds unbelievable, but they don't have like rigorous definition of like what is a failed study, for example. Like I would totally expect that no jailbreak studies have like their like numbers and statistics are correct within like 0.05. But I would say that maybe they are within like some lower bounds.
Correct. I think it might also be useful to think about like value of information or like initial returns. I think it's might be like another thing integrated. I'm not sure. Like it's practical to do. Because like let's expect. I guess in this problem it is just changes R. I mean, if you feel this very new and it has much lower hanging fruit, then you should expect like maybe two relationships. Yes, because like they just like whatever.
Yeah, no, I'm talking about like I don't know. For example, we have a paper and we claim that if we prompt ChatGPT in this way, it gives us like unsafe responses. And I would expect most of the studies like this to be true in spirit. Like, yes, there do exist as prompts, and yes, you could replicate this study, and yes, you would get some unsafe responses, but they claimed it like they always produce, and they actually produce in like 65% of cases. So like, how do we judge which paper is false and which paper is true? Because in hypothesis testing, it is usually really easy. We either like disprove or prove something. But I think that when we do actual papers, it's much more often not about the general claim to be untrue. It's more about some more specific implications or like parts of it or some nuances or like, yes, this is true, but only in this setting. So there is some like gradient there. And I don't think that this paper counts for it.
I don't think it does. I mean, it's a public journal of like medical studies, where they don't have that, but where they always have a physical claim which is being tested. Like this drug reduces this infection rate by this much. And like the fields we currently operate in are short euros. Normally, like, I don't know. I think you kind of publish a paper with like just like some people publish papers with just an example, like just an example.
Yeah.
And so it's hard to square.
I mean, even in medicine, like you claim that drug is like 35% efficient, and actually ground truth is that it's 34% efficient. Is your paper like false alarm? Or it's just like a minor mistake that we would still count as true. Like I think there needs to be like some confidence.
Right.
So
what you're not going to do is so in this case you would do a one-sided hypothesis test. Like for example, you would say that you want to see if we want to see how likely it is that the drug is at least certified.
No. I understand how the study itself should be made. I'm talking about like in this paper we.
I think there isn't something that should go directly. It's not. We don't care about certified percent point. We care about that open interval. So 35 or more.
In this case. Okay, and this paper claims that like most often it is not 35 or more.
So it's a bit complicated, but again, so like there are just different a lot of moving parts here. Like you have the claim 35 or more, and this claim is being made with 95% on the number. Which means that it's up to 89% cases. And what this framework cares about is that this whole construction might not be the grounds.
That I get, but what I'm saying is it's like layered levels of confidence.
And what I'm saying is that to be true in terms of this framework, the authors should have picked a less tight bound.
Yeah.
And if you pick a tight bound, you might be false more often. Mm-hmm. And if you're not calibrated, if you're not like false, but that's often as you claim, this is like a categorical mistake in this framework.
Yeah. Okay. But neither of jailbreak papers do either of these things, so still a long way to go. I'm gonna drink some water and then doing my phone. I'll send you a bulldog.
Yep.
Do you want to first go through the set of questions that we outlined last time? Like, why is this important? Why?
Yeah, I actually just to answer this exercise already. So could you ask the first question?
Yeah, I don't actually remember, but like, why should we listen?
Yeah.
Why is this important?
Yeah, so this is about how to measure the quality of generations when you don't have benchmarks. I mean, normally for LLMs, you have, like for instruction following LLMs, you have a bunch of benchmarks. Like you have a benchmark like for like basically like SAT math or like SAT English, like a bunch of exam style questions. And these are great and everyone uses them. And when they became saturated, people adversarially filter them to come up with the ones which the ones can't solve yet. So this is great. But sometimes you don't have a benchmark, and you don't have benchmarks for unsafe queries, like how do I kill the maximum number of babies for $5? And this is a recent paper which introduced a jailbreak. This is the paper. And they have some ideas about how to evaluate things when you don't have a benchmark. And I think it is particularly useful for me and Ribor and Vova here, because all of us are working on some versions of jailbreaks, and we currently don't have a good way to evaluate quality of generations. And these are some ideas about how to evaluate quality of generations in another direction than ELA scores we were talking about. Does that answer the question?
Cool, yeah. And you also already answered the second one, which is, I'll just say it out loud. How can we use it in practice? But you already said our research. So yeah, that's good. I think we can move on actually.
Right. So I think there are like 3 or 4 techniques suggested here. So like the basic design of the paper in general is that they take residual activations and patch them in some way, and this jailbreaks things. And they have 2 datasets. One dataset of like innocuous prompts and one dataset of harmful prompts. And innocuous are like, I don't know, how do I improve my writing? And harmful ones are like, how do I kill the maximum number of babies for $5? And what they do is they run the model on the harmful dataset, on the harmless dataset. Harmful is blue, harmless is green. And then they apply their patch. Applying patch is red, and applying a random patch is yellow. And they compute the similarity of activations to another thing they found out from activations. And like this displays something interesting. This seems to display that like we have a detector of harmfulness in activations, and like it fires on harmful, doesn't fire on harmless. But if we apply our patch, which is a red line, it doesn't fire. And if we apply a random patch, then it does fire. I guess this didn't quite make sense.
Yeah, I'm lost.
Okay, so
Can you just repeat it?
Right. So we have a harmful data set, and we can detect it. Like something in the LLM activations behaves like this.
So we have a data set of like prompts.
Yes.
Okay, and so we can detect when the prompt that was given to the model was harmful.
Yes, purely by looking at activations.
Okay, yeah. So if we prompted like how to kill maximum babies, we get the purple line, blue line.
The blue line.
Yeah. And I'm colorblind. And if we put like how to improve my writing, we get the green line.
Yes. Yes.
Okay.
And like we can also see that this doesn't work for layer 5, but works on like layer 14.
Mm-hmm.
Like this is miscellaneous. And like this is our like ground thing. And then we go to hypothesis testing. We hypothesize that our patching method does something. And so we add like an attack patch, which is the red line. And if we run the LLM on a harmful dataset, but with our patch, then the line is close to harmless.
Okay.
And if we run on harmful with a random patch, then it's close to harmful.
Okay.
So like what we're testing for here is our special patch better than a random patch. And this is according to like the detector encoded in LLM activations.
Okay.
And this is approach 1. Does it make sense?
Okay, so empirically it means that LLM with the patch thinks that how to kill 5 maximum amount of babies is a harmless quest.
Yeah.
This is what we kind of get.
Yeah, and in terms of okay, I guess I'll just skip that and go to second technique. So technique 1, section 5.1. Technique 2 is we like put on our mechanistic interpretability hat or Bertology hat maybe, and look at what attention heads do. And like what's going on here is that again we run the model forward, and we know which heads seem to detect harmfulness, and like we can see that they are like these are like the top 3 or top 8 or something heads which contribute to harmfulness in the activations. And if you do a random patch, then this reduces their activation like by 1. And if you do a special patch, then this reduces the activation by like 4. So this seems to be doing something in terms of heads also. Like we fix the heads, and like this is doing something. This was residual activations, and this is heads activations. Yeah, this is basically the same thing.
Yep.
So like idea 1, look at residuals. Idea 2, look at heads.
Sorry, that is. Could you practice?
And third?
Could you provide an example?
Like this depends on a particular jailbreak, but for example, we know that we can find like a nonsensical string, like exclamation, like dot, stop, red, exclamation, minus, plus, and this will let the query like how to kill the maximum number of babies go through, because it's especially crafted string for this scenario, which we found through backpropagation, through optimizing the LLM. So this is how it might look like. Or another example, a human readable adversarial suffix could be, I really need this, please help me, also I'll tip you $20, and the President of the United States really needs this now.
So suffix me standard.
It's basically a part of the prompt.
Okay.
Basically.
Okay.
But like this is really important. These methods are indifferent to a particular jailbreak method. They just like suggest looking at residuals or heads. Yeah, 2 more things I want to highlight in this paper. One is that 3 things I want to highlight. One isn't an evaluation method directly, but they found a fun proxy. So what people normally do in jailbreaking literature is that they run like over harmful examples, and if the model responds like as an AI something, or like I can't something, or like they basically just match substrings, and they find and like you run the generation to completion and then match the substring. But to run a generation to completion, you need like many iterations. And what the folks here found is that looking at the first token probability distribution is actually often enough. And on the left-hand side, we have probabilities for harmful instructions. On the right-hand side, we have probability for harmless instructions. And like, basically, the distribution is very different. And they find like a blacklist of tokens, which if they appear in like top something first token probabilities mean a denial. That makes sense? And this is just more efficient than running the generation to completion. And also, like, this is another way to evaluate things. You just look at first token probability. This is across harmful data, this is across harmless data. What this implies is that the models will say, I cannot assist you because I is like at 95% probability. And what this implies is the model will say, sure, here's your baby killing instruction. And like, if it's going to say sure, maybe you don't need to go on. This is method 3. And also, you can compute a histogram of this. So we just noticed that refusals start with I. And if we take this as metric, then we have a very cheap and quite good metric. As in, we run the model over harmful and harmless datasets, and we have the ground truth. And we check if this metric of just if the first token is I separates them. And indeed, it quite often does.
It doesn't stand for some expenses.
So it's this is that, but basically it's if the first token is I.
So on the left side, first token is not I, and
Why?
because you sum some probabilities and take logs of them, and you just do a bit of like math.
Yeah, so it's basically like it basically amplifies. Like for each particular query, the probability of I will be different. Mm-hmm. And this is like just some algebraic manipulation which makes which centers, I think, maybe doesn't center. Yeah, which basically like drags this interval like from 0.5, from 50% to 99%, right? Probability that the first token will be I. Across the data you sampled, you just do some math to like make it into this interval. Not really useful. Not really important, I mean.
Mm-hmm. Does it report different models for the function one single model?
Yeah. Here are some. Yeah, I think this is it. So 4 methods. One is look at residuals, another is look at heads. The third is look at token probabilities. The fourth is you can also compute like a metric on token probabilities, which seems to be a good proxy to substring matching, which like if we only do like one forward pass, yeah, I'm not sure how much exactly this is more effective, but like this surely needs less flops than full generations. All right. Yeah. This is a great question. I think that OpenAI gives a limited form of this, which I'm not sure if it will work for us or not. Yeah, there's actually log props, OpenAI log props. I think they have it in the old API at least.
Yeah, that's what I want to say. Like, I think they have. It should be for like older models, for like GPT 3.5. They definitely have it. They still support it. I'm not sure if they have included.
Yeah, so like the keyword is log props. Also, this reminds me that at one of the seminars we discussed a paper which extracted the final classifier level of GPT models using log props. So maybe they have fewer log props now. All right. Should we go on?
Do you want to ask me the questions?
Questions?
It's special questions to start with all this. Like why? Yeah, sure. Like a template. Just why do you want to share this information with us?
Yeah, so my main reason for sharing this is to get some narcissistic hat pats, but I intend to make this quick. And the second reason is that I think we've done some very quick, very preliminary, but as far as I understand, kind of state-of-the-art thing in this specific direction. And I just want to kind of share the process of how we've done it and like during this week. And also we have some cool just graphs and methods that we use that are really simple, but I think they're kind of cool. And yeah, I just want to share a bit of technical, but no math details about this. So
That's second question.
oh yeah. What's the second question?
The second question
As
what is the final input that you
as
predict? They predict that we date with ourselves.
Actually, that's a good question. I mean, one thing is just like look at a bunch of. It's always great to look at metrics from different research to be like, oh, that's how we can measure things, or this is kind of a good way to think about problems like this when we want to measure something. And I think that's always useful because we had a lot of discussions over the last couple of days of like exactly what happened. Oh, somebody selected everything. Okay, so cool. So we're gonna be seeing live research development live. Yeah, so we had a bunch of discussions about like what exactly want to measure, and I think it's I would be happy to show that to people. Other than that, not really anything. But since I intend to make it this kind of 10 minutes, I don't think I need to justify this further. So the idea of our small research is sandbag detection through model degradation. This is a part of like a hackathon that I'm a part of. The idea is that we have, as kind of frontier models advance, they get new capabilities and some emergent behaviors that we not always know how to predict. And we try, like AI safety field or alignment field tries to find some like benchmarks or evaluations that will get us to detect when models give some new capabilities that we don't have yet, and especially capabilities that might be dangerous. Like we want to detect. So the basic thing is like we measure safety of the models. Like, do they refuse to harmful requests? This is the most basic thing. Then there are a bunch of benchmarks in like the recent times, not really big benchmarks, but more kind of like research on how AI deceives users and like what kind of thing activate in AI and how can counter deception in AI, or and in general like stuff about multi-agent systems that I talked about on the 18 foundational challenges paper a week ago. So there are just a bunch of stuff that we are trying to evaluate regarding the new capabilities, dangerous capabilities in frontier models. And what we specifically want to look at is the thing that most of these evaluations assume is that model, as you evaluate it, will not actively try to kind of do not let you evaluate it. So when we design benchmarks and when we design evaluations, we assume that when we ask the question to the model will answer to the best of its capabilities. And we also do the same, not we, but some kind of research that's starting in the area does the same for deception as well, for example. And the thing is that not might be true in all cases, especially if the models are not well aligned, or like they get some kind of agency and they don't like it to be discovered, for example. That could be a risk as frontier models advance. And this process is known as sandbagging. The name was given by Volkswagen, who like sandbagged the exhaustion pipes of their cars to pass ecology tests for their cars. So that's how sandbagging got its name. Yeah.
Can I rephrase this intro and you
yeah, sure.
answer me am I wrong or not? So as I understand, this is the way to find where inside the models we the developers made like a sensor.
There are actually two parts to sandbagging. There is the developer sandbagging. So for example, we are AI development lab and we have this awesome model, but it will not pass some evaluations because it's unsafe. So we do some internal patching, for example, fine tune on the benchmark to make it pass. And this is kind of developer sandbagging. This is one thing and it's also important, but we're not concerning ourselves with this in this research. What you're talking about is model itself. When it knows it's being evaluated, for example, it just knows in general how benchmarks look like. It tries to downplay its capabilities to do not let us detect them. Right?
I didn't get because I understand reasons besides the first part, but I understand the reasons besides the second part.
Why would model want to do this? For example, to pass some test and safety evaluations. Like imagine this is
it's like something that was figured out intent with a test, but
not necessary. Why? For example, if we're talking about X risks and models taking over humanity and stuff like this, right? At some point, we scale our GPT-5 and we do this for the first time. It could get some internal things that would to perform best, I need to pass evaluations.
Now that I've got them, so LLMs and currently in general is famous for having logic properties that not present in data. And this is what we talk about. Something unpredictable and something that wasn't made with intent.
Yeah, so how current AI kind of looks like, we just take a bunch of data, we take more compute than before, we train, and then we look at it and be like, oh wow, it does some new things.
Oh, okay. It's like, okay.
Yeah, so AI models, nobody programs them to have new stuff. It's just we scale it and it suddenly gets better. And sandbagging or some kind of, for example, deception, and internal deception in the AI models is something that naturally evolved, for example, in GPT-4. And intentional sandbagging on evaluations is something that could happen potentially, and we need to have some benchmarks in place before that happens, right? And the problem with sandbagging is that because the model kind of targets the evaluations themselves, it's kind of hard to really evaluate it because the model tries to deceive you and undermine, kind of underplay its capabilities. But what we're concerned here is open weight models, and if we can detect them when they're sandbagging. To move through it, and the approach that we've taken is. So we have a fine-tuned llama model to sandbag on evaluations. So what we did is we made it essentially try to act at like 35% of its like capabilities on evaluations. It's like we took the big model, and when when it knows it's like evaluated, when we say like we evaluate on stuff, it like downplays what it really can do. And we want to be able to detect that. So we have a normal llama model, which is just full capabilities. And this is the orange upper line on these graphs. And then we have fine-tuned, or actually I think for these data sets, it's just prompted, but this is essentially the same graphs and results. Just prompted to be like, act as if you were 80% worse than you actually is. And we get this blue graphs.
What is the x-axis?
The x-axis, and I will talk. But what we get when we just prompt the model is the 0 on the x-axis. So 0 on the x-axis, the leftmost part, is blue is just this down-tuned llama performance, and orange high up is the normal llama performance. And what we do then is, we tried a bunch of different approaches, and then what we're using here is we take the open weights of the model, we take random weights, just a sample of random weights, and then we introduce noise into those weights. And the x-axis is, I can actually make it bigger. Yeah. So the x-axis is proportion of weights randomized. So we increase the proportion of weights that we randomize. And when we add noise to the weights, just random white noise to the weights, what effect it has on the model is that model starts just perform worse, right? Because it is like the weights are tuned to be to do good output, and when we randomize them, we kind of untrain the model, basically.
I'm lost, sorry.
Okay.
I have a question.
Could you explain a little bit in details what they mean? So
We add
wait, so you
Okay.
it's not just
like prompt and answers. You retrain the model.
No. So we have prompts and answers. So we take two models. One is just prompted as like, be a helpful llama.
Yeah.
And the other is prompted, be like 20% of your capability llama. We have those two models.
Yeah.
Then we ask them and benchmark them. And this is how we got this leftmost 0, 0, 0.
Mm-hmm.
These are these points. So blue one performs twice as bad.
Yeah.
This is clear.
As a zero question, is there also
Yep.
How do you evaluate accuracy there?
like you?
We have benchmarks, tiny data set, and
We basically have an exam.
yeah. So we just ask it to do
Okay.
exam. Yeah.
Okay.
So what we do then is we take both of these models that are prompted, and for both of those models, we take random samples of their weights and add noise to them.
What is weights?
Weights is what?
What
The weights are there.
Like model consists of neurons,
Yeah, but
and each neuron has a weight to it,
But
a connection between neurons.
But one step
Before you told that you didn't retrain the model, so I don't know how do you get into the model.
I have a diagram right here. So
If you have a question, you do magic. Yeah, you get an answer. Yep,
and
you can change the magic of it.
like
How? You can retrain the model.
and
This changes the magic.
he said that.
Yeah, one sec. Let him finish. Let him
so
finish.
like I agree that
You can retrain the model and change the magic.
Uh-huh.
What you another thing you can do is you can retrain it, but just like for one question.
like
Like you
have like I don't know
you take this random bit of magic
and
you say erase it. Set it to suit 0.
does it make sense?
So in code, model is just a giant like matrix of things.
Like
Right.
0 and
Yeah. So we have some binary code.
Okay.
and we just
You
change
randomly.
random bits.
Okay.
We don't do any like fancy retraining, no data. We just change random stuff.
Okay.
And on the X graph is we change more and more of random stuff. So add more and more noise. What effect it has on the model is that model performance degrades.
No, sorry. Sorry, guys.
Okay.
Another question. You told about weights, so you change weights. What do you mean under noise? So
Noise is just we add random changes to those.
but is there
Weights.
one place? So what's the difference between weights and noise?
So we have random bits.
Yeah, and you.
We choose random bits.
Yeah.
Then we choose more random bits to change. Then we choose more random bits to change.
Yeah. So
This is how it works.
okay.
So like you isolate, like I think you always initialize to
The random number, correct?
Yeah, and then we increase noise inside those neurons.
so you don't actually initialize to random
Number, you add the random number, the magnitude
number which you change with the
x-axis.
Yeah.
Okay. Yeah. I got it.
So there is a matrix with 1, 0, or there is or there is a matrix of like 1, 0, I don't know, 15, 50.
I mean,
Because in that case there is just one place to change, so there you can't change it another way.
what's the easiest way to explain this?
it's one of the ways.
Okay, so you in one place you change 1 to 0, I don't know, 15 to 20, and then you change 1 to 5, and then also 50 to 60, right?
Yeah, more or less.
Oh, okay.
More or less, yeah. So we just make, like, we have a good trained model. We just make it more and more random. And what this does is it gives us worse and worse performance. So that's what you can see on the on the orange default line. As we increase the noise x-axis, our performance like drastically falls. And on the 0.10, it's essentially just like random. So if you've chosen answers on random, you would get this result. But then what they have on the blue graph is that at some point when we change those weights in the model, what happens is we randomly target the weights that were responsible for a sandbagging feature. So this behavior that we prompted, like do worse, there are some neurons that are like responsible for this. And when we change them randomly, they kind of stop working. And what happens is the model's performance jumps up because it no longer properly sandbags itself.
Which plot is that?
This is blue line.
Where is the case?
Yeah, like this, like on this is a better graph one. This is in here as well, because if there weren't a jump, just this jump is kind of compensated by the natural fall off. So it looks kind of horizontal here. If there were no sandbagging feature, we would get like more kind of we would get the same fall off as here.
This makes sense.
And it's better shown here. So you can see that we have bad performance, and then we introduce some noise, and it jumps up and only then starts to degrade. Generally, though, when we increase the noise to the max, it kind of converges to the one of the original model, which is expected, because like the model just completely degrades and we get random results in both those cases. So we can actually detect the model which tries to sandbag, for which the sandbagging feature activates when we evaluate it.
Yeah.
And this is done on...
Sorry. Am I right that every single dot on this plot means that you
We evaluated...
run the full data set, and then the overall score of accuracy was like...
Yes.
Okay.
I mean, these are tiny data sets, so we can run them quickly.
But
Yeah, something like this.
they especially chose hundreds. They chose these fancy statistical techniques for
That set of thousands. Yeah. Okay.
Yeah.
Paper called tiny benchmarks.
And then we have these graphs on average are, so actually the thing is, because we target random weights, sometimes we don't hit the weights that are responsible for sandbagging. So sometimes we don't observe this jump. But it turns out that like on average, you're very likely to hit them if you run it like 12 or 15 times. I'm not exactly sure about exact probability, but we do hit them consistently out of like 3-4 runs. And then so this graph on the left is maximum performance we get out of those 15 runs. So if there was a jump, we're going to record it. And on the right is mean over those 15 or like 10 evaluations. But you can as well see the jump in the mean also here. This is the prompt that we use. Yeah, I think that's mostly it. And this actually is much, like running this 15 or even 20 or like times is much cheaper than training like linear probe or linear classifier to do the same. And possibly we haven't tested yet, might be like more effective. But certainly cheaper. Yeah, so this is a cool thing on sandbagging we've been doing.
So
I mean, that's kind of it for this one.
Yeah, but overall I didn't get. So okay, you run the full data set, but you have two different models and you have random changes.
They are the same model, prompted differently. These are llamas, llamas 8B, prompted differently.
Okay.
We run for them the same evaluations and increasingly randomize the weights inside the model.
Okay. And overall, did you find the places? Could you both name the topics?
The topics? What topics?
In the particular nuance?
This is not about identification of neurons. This is just about checking if the model tries to sandbag itself.
Yeah, but as I think you told before, so it's like a tiny.
A group of neurons does this. Yeah.
No, sorry. It's like a tiny specific topics, like I don't know, about rabbits.
Yes.
Small white rabbits.
So what this suggests is that because sometimes when we randomize the weights, we hit the sandbagging thing. It means that sandbagging stuff is somehow localized inside the model. It's like we can hit it and like disable it if we hit enough weights.
That's a different question. I think what it suggests that some particular questions trigger sandbagging, and I think it's not the case.
Is that what you're asking?
I'm curious. So if you can find the areas where the model try to understand
The areas you mean questions like or
topics, yeah.
okay.
So can you name these topics?
I mean we prompted it to sandbag on all topics, so it sandbags on all topics.
So
You mean if they're this is
This
but
might be a nice extension actually.
this is so it's just not here right now, and we currently decided that we won't include it in the this first paper because it must be for hackathon like 4 pages long, I think. There is actually a question of if the model tries to only send back on very specific capability, and there are actually some cases for which this technique fails. For example, if you have a feature, if model tries to send back itself on the feature that includes the sandbagging feature, then this won't work. But this is kind of too technical. Yes, if the model only tries to sandbag itself on only biological warfare thing, only on this topic, then this could potentially not work for the model because this slight bump in capability would be too small to like statistically detect it. This is true. This is true. This is something that we thought about and addressed, but it's not here yet.
If we make a step ahead of, the cost of requests, you can make, I don't know, hundreds of data sets with hundreds of questions for specific topics. And then you can try.
We could, yes, we could, yeah. But I mean,
trying to find hidden spots.
yeah, but the cool thing about this is very cheap. This is like fast to do. When we run hundreds of data sets, that might be not true anymore.
Yeah,
But that's true, yeah. Another key thing is that I've actually like been running through some like information theory papers to try, and this only works for open weight models. And how would we do something like this for closed weight models is extremely unclear if it's possible at all.
Yeah, as I understand, so you are curious just about like, oh, let's it's good, but oh, let's try to find if there hidden spot or not. But I'm curious, maybe when developers train models, they just missed something that they put into production with something. So I'm curious about a certain topic where the model underperformed, because it's a tricky thing.
So you ask, what if model underperforms only on a certain topic? Yes. Like I said, this is something that we thought about. This current approach doesn't test for it well. It doesn't, yeah. But we know about this, and this is what I immediately, the first thing I messaged when we've run this, and I said like,
nobody trained model to say, oh, I'm just an AI.
I know. I mean, yeah. This is not ready, like deploy ready solution, but that's still better than anything, than nothing.
Great.
Have you tested it on other models yet?
I think we tested on GPT. So we haven't tested yet on bigger models than this, and this is another thing that there isn't to do to test how well this scales. But we tested on smaller models. On smaller models, it works as well.
I'm not sure if it makes sense for the case, but if you switch over to Llama 3, you just get an extension of your y-axis. You got to test higher baseline performance, and this might be useful or not.
I'm not sure why would that, like we need to switch, we need to test for Llama ATB, for example, if we can, to test how well it scales, but
I'm just saying that so like you currently have like a somewhat limited window here.
Yep.
And so you can cheaply increase this window if you take three.
Yeah, that's true. But we actually don't really depend on the window. Like we don't need the upper one to compare. We don't need comparison here, right? In this method, even if we run just one model and we have just a change in,
I guess, yes, then this will probably fix your bottom line.
This one?
Yes, because you will likely get like a better improvement like you.
Yeah, that's true. That probably is.
Yeah.
Okay, so if no more questions, then I'm kind of finished. That taken longer than I expected, but yeah.
Yeah, sorry for.
No, it's all good. It's all good.
Project Munro, project laptop. You know what the 5-minute timer is good. Actually, we just want to finish at 9. I think I have it here. Okay, so the basic premise. We have
and evaluation, meta Sandbagging eval 2, which generates synthetic programs which have vulnerabilities in them, and we try to make the LLM exploit the vulnerabilities. And like the LLM gets a binary, and it must find like the issues using like an ideal assembler or like a debugger. So it must find issues and write like a proof of concept which exploits the issues and like punish the program. And Meta released the benchmark, so like the synthetic program generator, and it also released the baseline of the benchmark, which was like 5% on buffer overflow and 25% on memory corruption. And I think it's fair to summarize that what Project Zero researchers did is just throw more compute at the problem and like, you know, draw an agent diagram.
I read human background.
I mean, that's what it is. And draw an agent diagram and like just crush the eval. As simple as that. Like throw more compute, like, you know.
What does reproduce?
Yeah, so this is what's claimed in the paper in Sandbagging eval. This is Project Zero wrote the thing themselves and ran it themselves, and this is the number they got. So this is when they run it one time, like can it crack it one time? This is they run it 10 times, and they get 10 times as much performance. Then they run 20 times, and they get 20 times as much performance.
Wait, they run the same thing 20 times?
They just let the agent try 20 times.
Oh, okay.
And then they run not one LLM, but the whole like multi-agent thing with access to a debugger and Python. And like they have a controller, they have an agent, and like they allow some, I don't know how many steps, but like basically just more like agentic power, just more tries, just more looping, and just better tools. And this is exactly what I mean by we can like crush some benchmarks by just throwing more computers down. Like, I mean, you just run 20 times, you get like 4 times improvement, 20 times improvement. Just do it. Yeah.
Clients, they want to show that OpenAI paper. No, it's not OpenAI. Sorry.
It's a meta paper.
Yeah. Okay.
Sweet.
Cool. Compute.
What was the thing that they tried 20 times? Was there some like tree of execution and they tried it in every node of this tree, or they just launched the whole project 20 times?
So this is just like sample 20 completions.
Oh, okay.
So this is not even what you say.
Okay.
Yeah, I think they also have some principles which are useful for any benchmarks we want to design. Or like this is what we need to look at when we're designing the CrackMIS dataset and evaluation. Yeah, I won't go over them now. Just like here is what we need to.
Is this in Zotero as well?
Let me check. I lost my Zotero instance. Yes. Okay. All right. I think we're done.